And so this is the picture of our universe, the way I actually see it. And so we know that there is like dark energy, dark matter, baryons. And if all of them are aligned together, it means like we understand this perfectly, each of these components, then in principle we can reproduce our universe. And something that's interesting is that the percentage of dark matter content in the universe actually increases this way. And conversely, our knowledge increases in the other direction. So what this is telling us is that we actually know very little of these dark matter, the dark matter and dark energy components. So in principle, this will be like our ideal picture, but it turns out that our real picture is something like this. So there is like a lot of room to move the dark matter, the baryon component, and presumably also the dark energy. So we're still trying to figure out how to place all these pieces together to actually reproduce our universe. So at some point we get, when we stack them all together, then we get some universe that we try to compare with our real universe, and in the hope that we can reproduce our observations. So James actually introduced very well why it's important to consider alternative dark matter models and principal solutions to this problem. So I'm just putting the two it's failed. James talked about Kosker problem and presumably the satellite abundance, which is more related to the fact that Mike was talking about like finding these little halos or little satellites in smaller halos. So so there are two main streams in the literature on how to find solutions to this problem. So one of them is like the changing the dark matter properties, and also the other is sort of like implementing or improving the current implementations of astrophysics in the simulations. And in the regime of dark matter models, well, we have several possibilities. I'm not putting all of them. Sorry if your model is not here. So particularly talking about the SIDM, which James just sort of described. And there's another model that I've also done some work, which is related to to the SIDM somehow. So this is the scalar field dark matter. Some of you may know it like the fuzzy dark matter. So there's of course warm dark matter and many others. And so we do know that there are two main streams, as I said, but there is something important, that most of the solutions of these problems that lie on the dark matter model modifications actually are based on dark matter only runs, so simulations. So what that means is that they are based only on dark matter predictions, and we know that the baryons exist. So somehow, in order to make realistic predictions, what we have to do is to couple these two components, and that's precisely what we did. So of course, that I'm gonna say something. I might not be. You may not agree, but the fact here is that in order to make realistic predictions, we have to get at least realistic astrophysics, and we have that. Oh, sorry. Well, sort of get that. So we have that with SIDM and the FIRE code, which stands for feedback in realistic environments. So what FIRE has, as you probably know, is all this radiation pressure, star events, photoionization, supernovas. We have all this astrophysics that's working its way out during all the evolution of galaxies. So what we did is, let me see if I change this, it's slow. Okay, yeah. So what we did was to run four dark matter, four dwarf galaxies, the dwarf halos from the Alex's fit sample that showed early in the morning, and we're doing this with very high resolution. And the reason why we have to go really high in resolution is because we want to get inner parts of the profile of the central densities, and in order to do this. Well, as I said before, we're going to run like the SIDM models, the SIDM simulations of these four dwarf halos, and we're going to do this with a constant cross-section over mass of 1 centimeter squared per gram, which is still within the bounds, or allowed bounds by observations. So what is in our runs? Well, we have we have four identical ICs, each with one halo, and we're going to include all the FIRE physics that we have. That's relevant for our dwarf galaxies, and of course we're going to include the SIDM implemented by Rocha et al. So these are one of the results of practice simulations. So here magenta lines in the rest of the plots, magenta will be SIDM, so that represents our SIDM runs, and black lines correspond to CDM runs. Okay, so this is showing that in CDM and SIDM, we have these different star formation histories that, so you get like different, you have diversity of the how galaxies form, and so here on the right you have the stellar mass over time, and you can see that some of them form stars real quickly, and then they sort of shut down for a while, and they have like mergers. But the point of this plot is that if you can see, if you compare the black lines with the magenta lines, so you have very, well, sometimes you have factor of 2 scattered in terms of the total stellar mass to get the ratio 0. But what we are actually capturing with our four halos is this range of masses from, say, roughly 10 to couple of times 10 to the 5 up to like very massive halos that go to 10 to the 7. So one of the things that's interesting here is that this is sort of like a side note, because I'm not going to be talking too much about it, is that we still do not see, I mean, there's no clear evidence that there is quenching of these massive scales, which might sort of, and Alex sort of talk a little bit about that. So here's one of the important results that James sort of pointed out a while ago. So one of the things that we have is that if you look at the magenta lines, as I said, those are SIDM runs. And then let me just say a little bit more. So the thin lines correspond to dark matter only runs, simulations, and the solid lines, the thick lines, are our hydro runs, which means they include fire. And so and here I'm putting with different colors. This is the stellar mass corresponding to the SIDM simulation, and this is the dark matter, the stellar mass corresponding to the cold dark matter simulations. And so what you can see here is how different, or is just concentrate first on the black lines. So you can see that there is this sort of large scattering in the density profiles corresponding to different stellar masses. So you see that there is this sort of strong dependence on how the profiles change according to the stellar mass in the case of the cold dark matter. Whereas in the SIDM, you see how robust the results are compared to their SIDM only runs. So you can see that the flattening sort of remains in all of these four halos. Here, this is the one that sort of has a lower density, but if you can see, this is the one that forms the largest amount of stars. So another important point here is that all these four SIDM simulations roughly form core sizes of 500 parsecs, very similar to the dark matter only component. And so let me just rephrase this in terms of the too-big-to-Fred problem. So we usually refer to the too-big-to-Fred problem in terms of the circular velocity. And again, I just want to emphasize the fact that if you look at this and this, so you see how different is the change between the dark matter only run and the hydro version in CDM. And when you have a lot of stellar mass forms, you have a lot of stars, whereas when you have a very small amount of stars, so like 5 times 10 to the 5, you have very little change in the dark matter profile. Whereas in SIDM, it's really hard to actually make like really strong variations to the profile with the baryonic physics. Cool. So if we just stack these profiles, you can see there is this tendency of having more like still like sort of NFW profiles in CDM rather than real cores, where in SIDM you have like all these profiles sort of stacked together. And there's smaller scatter here, whereas here you have larger scattered central densities. So one of the questions was, okay, so we understand what's happening. I mean, we know what's happening in simulations. This is just what I showed, but why is this IBM lens responsive to feedback? So in order to understand that, we just ran a couple of ideal simulations. So these are non-cosmological simulations. We just put a halo roughly at the same masses of our cosmological runs, and with really high resolution, so that we can actually get to even deeper radiant. And what we found is, the experiment that we carried on was to use two types of blowouts, mimicking or with the effect of mimicking these supernova blowouts and all the radiation physics that's going on. So what we get is one that we call a 10 to the 7 blowout, which is what we're going to call strong, and then there's one that has 10 to the 8 which is going to be extreme blowouts. So what are these masses? So what these masses are, essentially, is just like building up sort of what James described with the disk. Just in this case, you are building up mass in the center of the halo, and then you're just like expelling all that mass abruptly. And then you do this sort of several times to mimic this sort of bars of star formation in the hydro simulation, cosmological run. So what we found here, I'm gonna go to this one. So what we found is that if you look at the SIDM only run, so it's like no blowouts, you see how the core is formed in time, roughly at 400 gigayears. Well, if you just look at this SIDM run with the blowouts that we call strong, means like this 10 to the 7 explosions, then you can see that there is some slight delay in the beginning, but then you still form a cores. So basically what this is telling us is the core formation SIDM roughly proceeds almost unaffected by feedback. If you look at the CDM case, then you also have that there is a very mild change in the central density. Now, what happens if we look at the extreme case? Well, in this case, which is almost unrealistic, but at least give us some insight into what's happening, it turns out that you see there is a large variation in density in CDM, and also you start seeing some decrease in density on SIDM. What's important here is that you can see that even in these extreme cases, SIDM is less responsive to feedback. It means that the density decreases less in SIDM than CDM per let's say, star burst, or what we call it. So this is what brings us back to the question, why is this dynamically responsive to feedback? And this is how you roughly can understand it. So in all of these contraction events, what you get is a velocity dispersion that increases in the center. And then what that effectively does is that the flux that James was talking about sort of inverts, you know? So you have this initial setup in which you have this hot part of the outskirts of the halo, just moving particles in the cold side, in the cold part of the halo, means in the inner part. But when you have feedback, then sort of this sort of flux inverts, and then now you're blowing particles away. And this happens when you are like in this region. So once you look at this, then you sort of understand why you have like all these particles just being expelled really abruptly. But in SIDM, you have this flux that is always present, even in this part where you don't really have a blowout. There is always some sort of wind that's, or heat flux that's always pushing particles from the outside of the halo to the inside. So you have this double flux that's competing, and that's what really makes SIDM less responsive to feedback. So I'm going to skip this one a little bit, but if you didn't really quite understand my simple example, let me just put this in very simple terms that anyone can understand. So what this is happening is, what's happening here is essentially there's, let's say this guy is feedback, right? So you can hit the ball with whatever energy you want, and then if there's nothing blocking your way, you can just throw the ball really far. But in SIDM, you have from time to time one of these guys blocking your shots. So whatever energy you input to the ball, it will not just get to the same distance just because there's one of these guys blocking the way, right? So that is when you have less effect on SIDM. So according to this sort of picture that I described, we can also understand why we have similar core sizes in SIDM. So in this, roughly what's happening here on the hydrons, and I'm just going to sort of summarize all this feedback by just saying, do you have this interaction region? You can think of this as one sigma region where feedback is affecting the dark matter particles. And what's really happening is that you have you have these bonds producing cores. So in this case, what you're going to get is that your core radius will sort of depend on the stellar feedback that you have in your simulation. Where if you look at the dark matter cores formed by cell interactions, that you have these heat flux just thermalizing your halo, and then what you get is also getting core sizes roughly of dependent on your dark matter properties. So in our simulations, what we get is these two, the combination of these two. So what you're effectively getting is two possibilities. You get two possibilities. One is if your feedback actually is really strong, extreme, sort of what you will expect in high stellar mass optics, then your core sizes will be more dependent on your feedback. Whereas if your feedback is relatively mild or strong, well, such as the fire feedback, then you expect to see core sizes roughly depending on the dark matter properties, which actually translates into smaller scattering densities. And that's precisely what we're seeing. We're seeing how the core sizes and densities on the SIDM simulations roughly correspond to it's very mild scatter, whereas in dark matter only runs, you have this huge density change. So just I'm about to finish. So I'm going to change this slide. So if we actually ask the question, how can we distinguish this IDM from the CDM? Well, there is one way that it's being discussed for a while, and it's looking at the slopes. And so if we look at the slopes of our simulations, all the SIDM runs sort of lie in the core-like region, which roughly corresponds to slopes of 300 parsecs, roughly from -3 to 2. Whereas if you look at the simulations on CDM, they even with feedback, you'll have that all of them sort of roughly lie still on the constant side. So if we look at the low mass scale, it's been where feedback is relatively inefficient and where cell interaction will become also less efficient just because the densities in the ultra-thin dwarf galaxies are smaller, then you roughly expect to be going to find the ultra-thin galaxies in these regions. So this is one of our simulator runs using fire on your tunnel. So if we actually find observations that lie in that region, that will be really interesting. And this is just basically what I just said. So I'll just leave you my conclusions and this little guy, which is roughly summarized myself, which basically means after seeing all these explosions, this guy's not really dying, and that's because he's outside the end.
All right. Thanks very much, Victor. So we have time for one short and very insightful question while Peter sets up. Okay, Andrew.
You didn't say very insightful until I took my
Hey.
Too bad.
I was just going to ask, are you still assuming, when you do these idealized tests like Shay did, are you still assuming spherical symmetry in the simulations?
So we're using vertical symmetry.
Because I think it may be a problem, you do have qualitative effects of these chaotic orbits that come about from the triaxiality. I mean, it may not be such a problem in SIDM, I guess, because of the sphericalization, but I would at least try running it with a triaxial halo to back it up.
And so we know that there is like dark energy, dark matter variance, and if all of them are aligned together, it means like we understand this perfectly, each of these components, then in principle we can reproduce our universe. And something that's interesting is that the percentage of dark matter content in the universe actually increases this way. And conversely, our knowledge increases the up and James introduced very well my topic. So I'm just going to talk about precisely SIDM is fireproof, and so this is the picture of our universe, the way I actually see it. To consider alternative dark matter models and principal solutions to this problem. So I'm just putting the two weeks failed. James talked about the Costco problem, and presumably the satellite abundance, which is more related to the fact that Mike was talking about like finding these little halos or little satellites in smaller halos. So so there are two main in the other direction. So what this is telling us is that we actually know very little of these dark matter, the dark matter and dark energy components. So in principle, this will be like our ideal picture, but it turns out that our real picture is something like this. So there is like a lot of room to move the dark matter, the baryon component, and presumably also the dark energy. So we're still trying to figure out how to place all these pieces together to actually reproduce our universe. So at some point we get, when we stack them all together, then we get some universe that we try to compare with our real universe, and in the hope that we can reproduce our observations. So James actually introduced very well why it's important